All right. Are you ready for it? We have arrived at Advanced TCP/IP IP Subnetting Part 1. If you haven't looked at the bottom of the window yet, this video will take a little extra time because I'm going to fully walk through multiple examples of subnetting based on network requirements. 4 different ones to be exact, and then leave you with a bunch of practice to do on your own. Now, one of the things that I've found is the best way to teach subnetting is not just to start talking about the advanced pieces of it right away and say, oh, this is what subnetting does and binary addition and all that. It's more so to apply it to the real world. So you can see that we have 4 separate scenarios, 4 different network requirements that we're going to walk through one by one as we determine how to break a network into multiple subnetworks one by one. Let's get going. Let's start off with network scenario number 1. We have an organization. This organization has purchased a Class C address 216.21.5.0. So they've purchased that from the powers that be, the internet, and they now want to use it to address this network. And this is a picture of their network. Now, here's the trouble, and this is why we need subnetting. They purchased a Class C network, and let me just write it over here, 216.21.5.0. Now, when they bought that, it's a Class C network, so the subnet mask is this. And the question I have is, how many networks do they get from that? Well, looking at it, it's just 1. We draw our line boundary right there, and 216.21.5 represents the 1 network they get. That's their network. And this over here represents the host. It goes from 0 to 255 maximum, where you can't use 0 and you can't use 255. You get everything in between. You can't use the first and last address from the network range. So we have 254 hosts on 1 network. Now look at their network diagram. How many networks do they need? Well, let's number them. 1, 2, 3, and a lot of people forget these, 4, and 5. Remember, every interface of a router is a network. So we need a network address or a subnetwork, a network, for every single one of these locations. Here's maybe an office with an Ethernet switch. Maybe that's in Arizona. We have an office across the WAN link to California. The WAN link to get there is considered a network, and the office itself. Then we have a WAN link over from California to Florida, which we have an office right here and the WAN link itself to get there. So we have 1 network that we purchased, but we need to break it into 5. So we know our network requirements now. Now, here are the 3 steps of subnetting. Before we start working through this, let me give you a little disclaimer. First off, I wrote our network requirements up here. This was our Class C subnet mask that we needed, and we know that we need 5 networks or subnetworks based on what we saw on the previous slide. Now, the disclaimer that I have is that there are more ways to subnet than there probably are grains of sand on the seashore. I mean, literally, even myself, over the 12 years of teaching that I've been in, have taught this probably 6 or 7 different ways. And about 5 years ago, I came up with this little 3-step process that will work for just about any subnetting scenario you can throw at it, and you'll be able to figure out the answer. Now, the first time we work through this together, it's going to look a little weird. And you're going to go, I don't know about that. But I'm telling you, after about the 3rd or 4th example of this, you're going to start going, oh, I see how this is working. And between this and the following video, I hope to give you enough examples and practice that you can work on yourself so that you'll be able to master this skill and master it quickly. So, our first step in this subnetting scenario is to determine the number of networks and convert it to binary. We need to use the skill that we learned previously in the previous video of binary conversion. So we know that we need 5 networks. Let me write up our binary chart. 128, 64, 32, 16, 8, 4, 2, 1. So 5 as a binary number is nope, 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 nope. Yes, there's our first one, 4, 0, 1. So we know that 5 is 0, 0, 0, 0, 0, 5 zeros, 1, 0, 1. That's our binary equivalent. That's all there is to step 1. The second step is the big one. Reserve the bits in the subnet mask and find your increments. Now, I'm going to show you something, and I want to make sure that when you start working on this, you don't skip this step or this part of the step. It may seem tedious at first, but you will greatly appreciate this after a little bit. We need to write our original subnet mask right here in all binary. So 255.255.255.0 is class C. Now, what's 255 in binary? All ones. That's the biggest number we can have, right? So 8 ones dot, this is the whole subnet mask, 8 ones, 1, 2, 3, 4, 5, 6, 7, 8, dot, 8 more ones, 1, 2, 3, 4, 5, 6, 7, 8, dot, and now 0 in binary is just all zeros. 1, 2, 3, 4, 5, 6, 7, 8. Now I need to have you make a mental leap with me, a transition. We've been looking at subnet masks like this up till this point, and we've been looking at them in decimal format. Everywhere we see 255, we go, oh, well, that represents the network. So we know 216 represents part of the network. 255, oh, 21 is part of the network. So we've been relating 255 equals network, and wherever we see the 0, that represents the host. But here's the leap I need you to make. We need to start thinking in terms of binary. So can I say, wherever I see ones as binary numbers, that represents the network, and wherever I see zeros as binary numbers, that represents the host. Is that an okay leap to make? Good. So what the beauty of video recordings is I can say, good, we're all on the same page, and we are. So we have right here our 24 ones that represent the network and our 8 zeros. Now what's our goal here? Our goal is to create more networks, meaning we only have one network and I need to create more, 5 of them to be exact. Now how many bits does it take to get the number 5? 3 of them. 3 bits, right? You can't get the number 5 with any less than 3 bits. Now when I ask that question, I know you may have been thinking, well, 2 bits, right? Because there's only 2 ones there. But if you look at this, if you only have 2 bits, what's the biggest number you can get? 3, right? If 2 plus 1, you can't get the number 5. So I'm not looking, when I ask that question, for how many ones do I have. I literally want to know how many bits does it take to get the number 5, and that is 3 bits total. So transition that back over. Our goal in this step is to reserve the bits in the subnet mask and find your increment. So when I say reserve the bits in the mask, what I mean is I know that I can't get the number 5 with any less than 3 bits. And I know that network bits are ones. So what I need to do when I'm making this reservation is give myself 3 more network bits. So I pick up where the ones leave off and go 1, 2, 3. 0, 0, 0, 0, 0. Now, I know, you're looking at this going, whoa, wait a sec, that was a little weird. I'm not sure if I followed that the whole way. Don't worry, we'll get used to this as we go through it again and again and again. But let me just reiterate, our goal is to create more networks because we only have one. And we know that it takes 3 bits to get our 5 networks that we needed, and then partner that with, we know that network bits are 1 bits. It doesn't really matter that 5 was 101. I'm looking for 3 more network bits. So with that in mind, I just add 3 more right where my network bits leave off, left to right, 1, 2, 3. At this point in the problem, we already know what our subnet mask will be for the entire organization. It is 255, convert this back to decimal, .255. That's what this one is, dot 255, that's the third one, that's what we had originally, dot, and then we need to convert this last octet right here back to decimal. Now, again, using those skills from before, if we line that back up to the binary chart that says we've got 128, 164, 132, 0, 0, 0, 0, 0. So if I wanted to find out what this right there is in a decimal number, I would just take 128 plus 64 plus 32. And that, if we add that all together, will be 224. So our subnet mask that we get for our entire organization is 255.255.255.224. Now that's fantastic. We know what every single PC, what every single router, what every single switch, every single device in our organization that is on the network will use this subnet mask. Woohoo! You know, do the happy dance, but we don't know what that means yet. You know, great, we've got a subnet mask. That's a key part of the equation, but we need to figure out what that subnet mask means, and that's the second half of step 2. It says reserve the bits in the subnet mask. We just did that, and find your increment. The increment, this is the other weird part, is going to be the lowest network bit that you have converted back to a decimal number. So look at our network bits. Right here, this is a 128, right? 64 in decimal. 32, that is our lowest network bit converted back to a decimal number, 32. That is our increment. So with that in mind, we can move to step 3. Which says, use the increment to find your network ranges. This is where the subnet mask becomes meaningful to us. So, I just changed my pen color here. Step 3, I'm going to take what I started off with, meaning the address that I purchased, 216.21.5.0, and then just begin adding my increment. Now my increment right here, this 32, is in the 4th octet, so that's where I do my addition. 216.21.5.32. 216.21.5.64. You can see all I'm doing here is adding my increment. 216.21.5.96. That's 64 plus 32. And so on and so on and so on we go. What this is, when I'm looking at this, is the beginning of each network range. Now, all I have to do is fill in the end. What's the last IP address before I get to 216.21.5.32, which is this one right here? Well, it's not a trick question. 31. Just take one away from 32. Put this through. 216.21.5. Last IP address before 64 is 63. 216.21.5.95. And so on and so on and so on. We would go down and down and down until we found enough network ranges to fit our organization. These are actual reality to us. Meaning, let me do a quick sketch of that network diagram. The network diagram that organization had looks something like this, where we had 3 different networks that we were trying to address. Now what I can do is I can start assigning these network ranges to that organization. This one will address, I think this was Arizona that I put, the Arizona router, and they will use that range for this network right here. You can see what we've done is sacrifice the total number of hosts we have, or to get more networks. We originally had 254 hosts with our Class C address up here, and now we've sacrificed that and said, well, I'll have less hosts, but more networks. The second network range can go ahead and address, I believe this was California down here, and the third network range will address Florida up there in the upper right-hand corner. I won't draw the arrow across just so it doesn't get too messy. The fourth network range would address the WAN link. And the fifth network range, I didn't go that far because I ran out of space down here, but the fifth network range would address that WAN link right there. Those are the network ranges that I can assign to the devices. I would then assign IP addresses from these ranges to the computers in Arizona. I'd assign IP address from this range to the computers in California. This is the meaning of subnetting. Breaking our one network into multiple networks. We've got our new subnet mask that we use and our network ranges that can be assigned to the different devices. With that in place, I know at this point it's like, okay, I'm seeing that, still a little fuzzy. Let's do another example. Network scenario number 2. Instead of drawing this massive network, I just put our requirements in the upper right-hand corner. We have another organization that is using 195.5.20.0. It's a Class C network. And they need to break that one network, 195.5.20, into 50 subnetworks, or 50 smaller networks. It's a lot of networks. That's why I didn't want to draw a network diagram. So, let's work through the steps again. Number 1, determine the number of networks and convert that number to binary. 50 is how many networks we wanted, so I'll put our equals, and let's draw up our binary chart. 128, 64, 32, 16, 8, 4, 2, and 1. So 50 networks, 0, 0, 1. I can take 50 minus 32, and that would give me 4, 18. So 18 left over. So I'd have a 1 in the 16. That would leave me 2, 18 minus 16. So there's our 2, and that is our binary number. 0, 0, 1, 1, 0, 0, 1, 0. Now, let me ask a question. How many bits does it take to get the number 50? Well, looking at this number, I can just underline where the first one started and say that takes 1, 2, 3, 4, 5, 6 bits. Good. Because we're going to need that number when we do step 2. So step 2 now says reserve the bits in the subnet mask and find your increment. Again, don't skip this first part. It may seem tedious, but that is the key to seeing what bits you have to work with. Our original subnet mask is class C, so in binary, it's 8 ones, dot, 1, 2, 3, 4, 5, 6, 7, 8 ones, dot, 1, 2, 3, 4, 5, 6, 7, 8 ones, dot, and then the most critical piece, not all the ones, it's the zeros. 1, 2, 3, 4, 5, 6, 7, 8. Because the zeros is where we can do our subnetting. We were given a class C address, so we can't change any of those first 24 ones right there. We can only play with the last 8 zeros. So now we look at our requirements. It says reserve bits in the subnet mask and find your increment. Our organization wants to break this into 50 subnetworks. We know that it takes 6 bits to get the number 50, and we know that ones are network bits. We need to change our subnet mask to where we have 6 more ones. So we do that. 1, 2, 3, 4, 5, 6, and the other 2 can remain 0, 0, 0. We have stolen 6 network or 6 host bits and made them network bits to meet our requirements. Just like that, poof, we know what our subnet mask will be for our whole organization. It's 255.255.255 dot, and then we need to convert this last one back to decimal. So we use our binary to decimal and decimal to binary conversion skills, and I say I've got 128, 164, 132, 116, 18, 14, no 2s, no 1s. So I can, by the way, when you see this, you can approach it one of 2 ways. I can either add all these numbers together, 128, 64, 32, 16, 8, 4, 2, or 4, add all those up, and I would end up, if I did that addition, with the number 252. But that's a pretty long addition problem, adding all those values together. So one of the ways that I do this and find a little shortcut is I know if all of these are turned on to 1, it's what number? 255, right? That's the maximum number I can get. And I can look at this and go, oh, well, there is no 2s and there is no 1, so I can just do 255 minus 2 minus 1, or just add those together and just do a 255 minus 3 and get 252. So whatever way works easier in your mind for you, either doing addition, adding all those together, or knowing the maximum is 255 and just subtracting what's not turned on, that will give you your subnet mask. Now, I'm trying to think. Should I add another piece at this point? No, I'm not going to. Let's keep working through this. I'll add it once we're done with this problem. It says reserve the bits in the mask and find your increment. So we've got the mask. We've reserved the bits. Our increment is the lowest network bit, that guy, converted back to a decimal number. Now, if we look in binary, this is, or in decimal, this is 1, 2. That one is a 4. That is the decimal equivalent of the lowest network bit. That is our increment, and that is what we need to find our network ranges. So the last step will be finding our network ranges. We start with what we were given, 195.5.20.0. That's the address that we purchased from the powers that be, and we want to use to address our whole organization. So now I just need to start adding my increment in whatever octet it's in. I notice it's in the 4th octet right here, so I'll just do some simple math. 195.5.20.4. 195.5.20.8. And I'll just start shortcutting. .20, .12, .20, .16. You know, this is the same the whole way down. That is the start of every single network range that I have. Now let's fill in the end. I'll go back to the top. The last IP address before I get to 195.5.20.4 down here is .3. The last IP address before I get to 195.5.20.8 is .7. And down I go. .11 is the last one before 12. .15, same thing. 195.5.20.11, .15, and so on. I just keep on going. I think the next one would be .19 because .20 would be if I added 4 over here. And I would just keep finding all these network ranges. Now, let me fill in a little more information here about these network ranges. We've taken one Class C network, 195.5.20.0, with one network that could go all the way up to 255, and broken it into all these little subnetworks. Now, there is a price to pay whenever you do subnetting. Here it is. When we had one network, we couldn't use the very first or the last IP address, right? Because the very first IP address identified the network. That's known as the network ID. You cannot assign 195.5.0 or .20.0 to a PC or to a router or to any device because it identifies the network. We can't assign that IP address because that's the broadcast. Meaning if I wanted to send a broadcast to everybody in that network, I would send it to that IP address. So I cannot assign this IP address to any given host. Now what we've done is taken this one network and broken it down into many subnetworks. But when we do that, we cannot use the first IP address or the last IP address from every single network range. So I cannot assign 20.3 to a host because it's the broadcast for this first network right here. I cannot assign 20.7 to a host because that's the broadcast for the second network, and the third network, and the fourth network. I cannot assign the first or the last IP address from every single range to a host or router or switch or any device on that network. So what does that mean? That means when I really look at this, I have 1 through 2, 5 through 6, 9 through 10. I have 2 usable hosts per network that I can actually assign. 1 and 2, 5 and 6, 9 and 10 that I can actually give to a device. Now I know you might be looking at that going, that is stupid. Why would you ever have a network of 2 hosts? Now, with that being said, I can tell you that is the second most popular subnet mask in the world. I'm not kidding. The subnet mask that you just found, 255.255.255.252, which gives you 2 usable hosts per network, is the second most popular one in the world because it's perfect for those kind of networks right there. That is considered a point-to-point WAN link, meaning, think of the diagram we had before where we had, we've had some hosts over here and some hosts over here, and I said, but this is a network too. Well, that network will never have more than 2 hosts per network because there's only a point, I'll put .1, .2 to point network right here. So I could assign this first network to that point-to-point WAN link. I have another point-to-point WAN link right here. I could assign this second network. Maybe .5 is assigned to that router right there, and .6 is assigned to that router interface over there. That is a very popular subnet mask and very popular way to find network ranges for your WAN links. Now, with that being said, that is the second network scenario that we've gone through that is a Class C address. I'd like to add one more piece of information that we can gather from this. That is a different way to write the subnet mask. You can see that I have the Class C subnet mask right here, 255.255.255.0. Now, I don't know if I've written it this way in the past in this series, but you'll see this subnet mask, shorthand abbreviated a lot of times, a /24. Have you seen that before? When people write a Class C subnet mask up here, they might write it 195.5.20.0/24 instead of actually writing 255.255.255.0. That's technically known as CIDR notation. Many people call it bit notation or slash notation. There's a lot of names for it, but all it is shorthand for writing the subnet mask. And now that we have this problem sitting right in front of us, we can explain why this shorthand notation means the same thing. When you see slash in a number, that is literally the number of ones in the subnet mask when you convert it to binary. Seriously, look at this. Class C subnet mask, 255.255.255.0. If you converted 255 to binary, how many ones is that? 8. Same thing here. 8. Same thing there. 8. So if I take all of those ones and add them up, 8 plus 8 plus 8 is 24. It's shorthand. So if I were to look at a Class A subnet mask, that's 255.0.0.0, that is abbreviated as a /8. A Class B subnet mask, 255.255.0.0, is abbreviated as a /16. Class C is /24. That's the bit notation. You're just looking at how many ones, 8 plus 8, or just 8 up here, is in the subnet mask. And the same thing works for these custom subnet masks right here. 255.255.255.252 can be shorthand noted in CIDR notation or bit notation by saying, okay, we've got 8 ones there, 8 ones there, 8 ones there. That's 24, 25, 26, 27, 28, 29, 30. /30 is shorthand bit notation for 255.255.255.252. When you are working on a Cisco device, there are many show commands that will show you the subnet mask in that format, and there are many show commands that will show you the subnet mask in that format. So you need to be comfortable working with both. Same thing if you're preparing for the CCENT or CCNA exam, there are questions that will give you the subnet mask in both formats, one or the other. So you need to be very comfortable working with either one. So what I want to do as we work through these problems, we've got 2 more scenarios that I've got for this video that I want to work through. I want to show you the subnet mask both in decimal and bit notation so you can get comfortable working with either. Now, before we move on to network scenario number 3, I want to make a quick point. We just did 2 back-to-back network scenarios that are using Class C networks. I'm about to move into a Class B example. Now, don't worry, it's the same thing. It's same 3 steps, same process that you work through. But I want to make sure before you jump into this one that you are comfortable with the Class C examples we just talked about. So if you would like, what I would propose is to pause the video right here. If you're still feeling like you want to see those again, rewind it and do the Class C examples one more time. It's the beauty of video. Just watch me work through those 2 Class C examples, then come into this Class B. If you're feeling comfortable and you're ready for a Class B example, feel free to keep on watching. I just wanted to make sure I mentioned that we are moving into another class of problem, if you will. So here's our scenario. We are given a Class B network, 150.5.0.0. And the organization that we're working for has offered us a lucrative $16.3 million contract to break that into 100 subnetworks. As of right now, a Class B network, 150.5.0.0, 255.255.0.0. We've got one network, that's 150.5, and a whole bunch of hosts, 65,535, I believe, to be exact. And that's way too many hosts. We want to break that into 100 different subnetworks. That's our goal. So the process is the same. Number 1, determine the number of networks and convert to binary. 100 subnetworks, right? That in binary, let me just write up our chart, 128, 64, 32, 16, 8, 4, 2, 1. So we convert it to binary, there's 0, we can't subtract 128, so our first one goes right there. 100 minus 64, remember on Cisco exams there are no calculators, so that'll be 9, it'll be 6, 36, right? So we can take our 32, that'll leave us with 4, 0, 0, 1, 0, 0. So 100 as a binary number is 011001000. Now, let me freeze for a moment right there. I'm not all about teaching shortcuts, meaning you're going to find as you work through more and more examples, there's ways to cut time by doing shortcuts. But there is one thing I do want to show you, and that's how to save a little extra time right here. When I convert 100 to a binary number, remember, I'm not so much after the binary number itself as I am after how many bits did it take to get the number 100, right? Because that's what I'm wanting for this second step of the problem. That's why we do this binary conversion to start off with, is we want to know how many bits it takes to get the number 100. Now, as soon as I find where my first 1 goes, do I know how many bits it's going to take? Well, sure I do. As soon as I know that my first 1 is 64, I know that I'm going to have 1, 2, 3, 4, 5, 6, 7 bits. It doesn't matter what the rest of the binary comes out to. I know as soon as I know where that first 1 is, that it takes 7 bits to get the number 100. So a time-saving shortcut right there, as soon as you look and find out where your first 1 goes in the binary equation, you can stop. You don't have to figure out and do subtraction and find the rest of it because you know, stop right there. As soon as I know my first 1 is at 64, it takes 7 bits to get the number 100. If that shortcut helps you save some time, it's great. If it confuses you, forget I ever said it. Just figure out the whole binary number. But you'll get comfortable with it as you work through it a couple more times. Here's the second step. Reserve the bits in the subnet mask and find your increment. Now again, it becomes even more critical when you have a Class B example to write your subnet mask in all binary. 1, 2, 3, 4, 5, 6, 7, 8. That's our first 255. 8. There's our second 255. Now the host bits. 1, 2, 3, 4, 5, 6, 7, 8. Dot 1, 2, 3, 4, 5, 6, 7, 8. We have 16 network bits. It's a /16 subnet mask by default, and 16 host bits that are at our disposal. Now we're going back to our question. We want to take the Class B network and break it into 100 subnetworks. We know that it takes 6 bits to get the number 100, so we will pick up right where our 1s leave off. This is the key. Don't start, it's not a Class C example anymore. Don't start adding 1s over here. We pick up where the 1s leave off and say, I need, wait a sec, did I say 6 bits or 7 bits? 7 bits. 7 bits to get the number 100. Sorry. 1, 2, 3, 4, 5, 6, 7, 0, dot, and all these say 0. 0, 0, 0, 0, 0, 0, 0, 0. 8 zeros. There it is. Okay, 8 zeros. That is our new subnet mask when we're using a Class B example. Remember, it's the same as it was before. It's just now we're working in this third octet rather than the fourth because we started with a different subnet mask. So our new subnet mask, we now know that, is 255.255. If we were to convert this one back to decimal, we could either add all those up or just know that it's 255 minus we don't have a 1. It would be 254.0. So our new subnet mask is 255.255.254.0, or if we're writing it in slash notation, it would be a /23. We had our original 16 bits, 8 and 8 right there, and we just added 7 more. That's the 254 or the 7 bits right here. So you can just think of that as a /23 as shorthand notation. So that's the first part of step 2. Reserve the bits in the subnet mask and now find our increment. Our increment is the lowest network bit converted back to a decimal. Now don't start letting your mind go wild here because I know you might think, okay, well, 128's right there, so is this like 256 now and stuff like that? No. The increments restart every single octet. So it's very simple. This is a 1, this is a 2, 4, 8, the decimal. I'm looking for the lowest network bit converted back to a decimal number. That is simply a 2. Now, step 3. Use the increment to find our network ranges. Just like the previous example, we're going to write 150.5.0.0. That's the network that we started with, and now we just start adding our increment. But before I do, I've got to ask the question, what octet is the increment in? The third, right? This octet right here is where our increment is at. Before, when we were doing the Class C example, our increment was over here, and that's why we added the number to our fourth octet. But since now our increment's in our third octet, that's where our addition takes place. So we have 150.5.2.0, 150.5.4.0, .5.6.0, .5.8.0. Forgive my penmanship getting a little sloppy as I go down. It's 150.5 the whole way down, and so on and so on and so on. We just keep adding 2 to that number. Now we fill in our end range, and this is where it gets a little tricky. You look at this and ask the question, what is the last IP address before I get to 150.5.2.0? Well, you look at it and go 150.5.1, and be careful right here, because I know you might be thinking, well, 1.0, right? Well, remember, if we do 150.5.0.0 through 150.5.1. If I put a 0 right here, well, then that's where this first range ends, and the next one picks up at 2.0. So let me ask the question, what happens to the number 150.5.1.50 or 150.5.1.51 or 52, 53? What happens to all the 150.5.1 numbers? Well, if you go to 150.5.1.0 as your end, you lose all of them. You can't do that. Think of some weird twisted math problem. 150.5.2.0, that's where our next one starts. If we were to subtract 1 from that, the last possible IP address before we get to 2.0 is actually 1.255. This one goes through 150.5.3, that's the last one before we get to 4.0, .255. Again, the last IP address before we get to 4 is 3.255. Last IP address before we get to 6.0, 150.5.5.255. And so on and so on and so on we go. Does that make sense? It's kind of weird, but that's the last IP address before we get to 2 and 4 and 6 and 8 and so on and so on. It's going to be the 255 because that's how the binary works out. That is the answer to the problem. Now, there's a couple more pieces I want to add as we have walked through this problem. The first one is this. As you look at these network ranges, we now have a network range that shows 150.5.0.0 through 150.5.1.255. We know that we can't use the last IP address from that range, right, 1.255, because that's the broadcast, just like we saw in the previous one. We can't use the first one from each range either because that identifies the network. So those are unusable. Now, here's the question. I'm looking at that first range. That's where my arrow is drawing from. Somewhere within that range, I'm going to run into the IP address 150.5.0.255. Right? Do you see that? It's somewhere squished in the middle of that range. Can I actually assign that to a PC? Well, on that same token, before I answer that question, I'm also going to run into 150.5.1.0, somewhere in that range. You know, it's in between 0.0 and 1.255. That's an IP address in that range. Can I assign that one to a PC or to a router? The answer on both accounts is absolutely yes, you can. It's going to feel really weird when you're typing it in because we're geared in a decimal mindset. We're geared to think, oh, 255, you can't use that. That's a broadcast, right? You can't use that. And same thing, 1.0, oh, you can't use that. You can't use zeros. That's the network. That's thinking in a decimal mindset. Those addresses are right in the middle of this range. They are completely valid addresses. Like I said, it's going to feel really weird typing it in, but when you combine it with this subnet mask in your network properties field, it will work just fine. It's right in the middle. There's only one broadcast address and one network address for each range, and that is it. We circled them right there on the screen. Everything that's in that squishy Oreo center of that works just fine. That's something to get used to. And I want you to already begin envisioning, if you're preparing for the certification exam, a test question that says, which of the following addresses are valid and invalid? Select all that apply. Well, when you see this, you think, oh, well, that's invalid. Well, that's not true. You have to back up and say, well, what subnet mask are we working with first of all? Based on that subnet mask, you'll be able to figure out which ones are valid and invalid. So that's the first piece I wanted to add to this, is getting comfortable with those network ranges. The second piece that I want to add to this is, what if somebody really wanted to know, okay, I can see that, we wanted 100 networks, but, how many networks did this really give us? I mean, if we were to count them up, here's 1, here's 2, here's 3. If I wanted to know how many networks I could get using this subnet mask, is there an easy way to do that without adding all of these up, going through and writing all the ranges and then adding them up one by one? Well, the answer to that is also yes. We can figure that out by using a formula. And I know this is the first mathematical formula we've introduced here. It's known as the power formula. 2 to the power of x is the formula that I want you to remember, where X is actually the number of subnet bits. Now, if we look, we added 1, 2, 3, 4, 5, 6, 7 subnet bits. That's what we found right here. It takes 7 bits. So if we do 2 to the power of 7, that will tell us just how many subnets we're going to end up with if we were to count this all to the bottom. Now, that's a painful equation when you're on a certification exam and don't have a calculator in front of you. So let me do this. Let me show you 2 things. First off, I want to show you how to figure this out if you have a calculator. And second, I want to show you how to figure it out if you don't. If you have a calculator, let me bring this back into the screen. Just clear off what we've got here. If you have a calculator, just a Windows calculator, all I need to do is go 2, and then move over here to these fuchsia numbers, x caret y. We'll do 2 to the power of 7, and hit the equal sign, and that will tell us exactly how many networks we get. If we were to follow this all the way to the bottom, we would end up with 128, oops, I went out of the screen, 128 different subnets that we could break this into. That's the way to do it with a calculator. If you don't have a calculator, the way to do it is using your binary chart. You might remember when I talked in the binary conversion video, I said these are actually the power of 2. This one is 2 to the power of 0. Remember I said I don't know why 2 to the power of 0 is 1, but it is. Anything to the power of 0 is 1. So if you remember that, you can go, okay, 2 to the power of 1 is 2. 2 to the power of 2 is 4, 3, 4, 5, 6, 7. Aha, is 128. So I can look at 2 to the power of 7 and say that is 128 just by looking at my binary chart and realizing their powers of 2. Okay, are you comfortable with that? That is adding a couple pieces to this, finding out that in between these network ranges we have some odd numbers that are valid, and finding out the way that we can find how many networks we really get when we do subnetting. Using that same logic, let me just clear up some room. I'm looking at this screen right now thinking, how on earth can you learn anything from this mess? It's just a mess of numbers at this point. So let me just carve a little extra space out for myself so I can do some writing here. I just showed you the equation, the 2 to the power of x equation to find the number of networks. But what if you were asked, not for the number of networks, but how many hosts do I get in each one of those networks? Meaning, how many hosts do I get in between 150.5.0.0 and 150.5.1.255? Well, just looking at that, it's not very easy to just add those up and figure that out. So you can use that same equation, slightly different, to find the number of hosts. 2 to the power of x, but this time x is how many zeros? We were using ones to find how many networks we get. So 2 to the power of x, with zeros being the x this time, will tell us how many hosts we get. But remember, we have to do a -2 on there. We have to subtract 2 from whatever our value is, because we cannot use the last, nor can we use the first IP address from each range. That's why we subtract 2. So in our case, 2 to the power of x, x is 1, 2, 3, 4, 5, 6, 7, 8, 9 zeros. We have 9 zeros left over in our subnet mask. So 2 to the power of 9 minus 2 will give us that equation. Now again, if you've got your calculator, that makes it a lot easier. We can go 2 x caret y, this fuchsia one, 9 equals 512 minus 2, 510. So there are 510 hosts per network here. If you don't have a calculator in front of you, you can say, okay, well, I know 2 to the power of 7 is 128. You know where that leaves off. So 2 to the power of 8 is 128 times 2. That's 256. 2 to the power of 9 is 256 times 2, and that is 512. It'll take a little extra math if you don't have a calculator, but that will be able to tell you how many hosts per subnet you have. All right, I have one more network scenario to work through with you. And after seeing the Class B one, it shouldn't be too bad, although I've thrown an extra little twist in here. We now have a Class A example. We have the network 10.0.0.0, and we would like to break that into 5 500 networks. Wow. All right. Same 3 steps, same process, just a little bit bigger numbers. We've got step 1, determine the number of networks and convert to binary. So here's my hint for this one. 500 is, let's go ahead and write our binary table, 1, 2, 4, 8, 16, 32, 64, 128. Now, stop right there, because I know that, wait a second, I can't get the number 500 with 8 bits. I can only get 255, right? Right. So we need to keep going. 128, 256, I'm running out of room here, 512. Now immediately I look and I go, oh, 512 is bigger than 500. So my first one doesn't go there. I can't subtract 512 from 500. So my first one goes right there, 256. Now I could work that out and do 500 minus 256 and find the whole binary number for what 500 is. But remember, I just mentioned on the last slide, we're not after that binary number and exactly what it is. We just want to know how many bits did it take to get the number 500. And when I look and I go, oh, well, my first one went right there, I immediately know it took 1, 2, 3, 4, 5, 6, 7, 8, 9 bits to get the number 500. Good? All right. Second step, reserve the bits in the subnet mask and find your increment. Again, we now have a class A network, so I need to write that subnet mask in all binaries. 1, 2, 3, 4, 5, 6, 7, 8, dot, 1, 2, 3, 4, 5, 6, 7, 8, dot, 1, 2, 3, 4, 5, 6, 7, 8, dot, 1, 2, 3, 4, 5, 6, 7, 8. Trust me, it doesn't take you this long when you're not talking as you do it. It's hard to write and talk. So we have 255.0.0.0 written in all binary. I now need to ask, am I trying to get more networks here, or am I trying to get more hosts per network? Now I look at that and I say, well, I want more networks. Now I ask that question because in the next video I'm going to show you the second style of subnetting, which is host per network. So we say I wanted 500 networks. 500 networks need 9 bits, and I know network bits are the ones, so I'll pick up right where the ones leave off and go 1, 2, 3, 4, 5, 6, 7, 8, 8 bits per octet, dot 9. 1, 2, 3, 4, 5, 6, 7, dot, and then those all stay 0. So we actually bled past our octet. We moved into another octet. So I know my new subnet mask is 255 dot second octet is now 255 dot. Now if I convert that third octet to binary, what is it? Or wait, to decimal. It is 128 is a decimal number. 1000, all zeros. If we line that back up, that's 128. So that is our new subnet mask, or in bit notation, it's slash. We have 8 ones, that's 16, 17. Slash 17 is our subnet mask. Wow, that's new. Now, here's a unique part about it. What is our increment? Lowest network bit converted back to a decimal number. Well, that network bit is 128. Wow, weird. So our increment is the same as our subnet mask. You bet it is. So now we have all the pieces that we need to move on to step 3 and find our network ranges. This is where it's going to take a slightly different look, but like I'm doing, I'm adding more pieces on every single one of these problems. This is the last piece I need to add. So we have the increment to find our network ranges. We started with 10.0.0.0. Hang on. Let me get a different color here. I know. Colors don't matter, but to me they do. They stand out better. So 10.0.0.0 is what we were given and what we started with. Now we need to look back at this increment and identify what octet the increment is in. It's in octet number 3. So I can just go and add 128 to the third octet. 10.0.0.128.0. 10.0. Wait a sec. What happens if you add 128 to 128? 128 plus 128. That gives you 256. You can't have 256 in an IP address. Well, here's where I want to show you. Now, notice, first off, we added 8 network bits. I know we're going to get way more than two network ranges with 8 network bits. I mean, if we did 2 to the power of x, where x is 8, we get a whole bunch of networks that are at our disposal with this, at least 500. So I know that I can't stop right here. So let's fill in the end ranges. Just kind of draw a line. Let's see where things end. This would go, what would be the last IP address before we got to 10.0.128.0? Be 10.0.127.255. Right? This would go through 10. Well, let's do the math as if it worked, right? Let's say that this went to 256.0. Right, if we were just adding like we were before. What would be the last IP address before we got to 256.0? 10.0.255. That's the last one before you get there, right? .255. But we know that we can't have 256. So let's make a slight correction here. Erase that. When we have 255.255, if I were to do like a +1, think of this as, again, that weird twisted math problem. I know that I can't go to 256, so that'll zero it out, right? 255 plus 1 and carry the 1. So we have a +1 there. We can't have 256, so zero it out, carry the 1. And now I have like this 10.1.0.0. That's exactly what the next range starts at. 10.1.0.0, and then just keep adding our increment. 10.1.128.0. 10, instead of doing this all over again, I will now recognize and go, well, you can't have 256, so we move up to 10.2.0.0. Let's fill in some end ranges here. This will be 10.1.127.255. That's the last IP address before I get to 10.1.128. This goes through 10.1.255.255. Last IP address before I get to 10.2.0.0. And so on and so on and so on. We would go down and down and down the range. That's the tough one. I have to tell you, it takes a little logic and a little working through that to get it, but that is how you can find those network ranges, is just identifying where the next one starts and subtract 1 to find where the last one would end up ending. Before we end this video, I want to make sure that you get some practice, because doing subnetting, working through it again and again and again and again and again and again, is the only way that you're going to solidify this skill yourself. So what I have here is 4 problems to do on your own. I have 2 Class C examples, which are by far the most common subnetting styles, but then I have a Class B and a Class A example as well, and they do add their own little twist, break into 1,000 networks, break into 25 networks, and that sort of thing. So I want you to take some time, grab a piece of paper, and work through these problems so that you can make sure you can not only observe the skill being done on the screen, but do it yourself. Now, I know that examples or practice problems without being able to know if you're right or not are of no use. So what I've done is I've actually worked through these problems on my own and put up my result on nuggetlab.com. You'll actually see a file there named something like CCENT support files, or it'll have some identifier that you'll be able to quickly see CCENT something. And you can download that and you will be able to check your work and verify your answers. When I worked these out, I worked them out on just in a Microsoft Word document. I saved it as a PDF file so everybody can open it. And all I did was walk through the 3 steps. So I have the results of the 3 steps that you would be walking through. You can compare your answers to mine and make sure that you're on the right track. This is the first style of subnetting that we must master before you move into the next style in the next video. I know that this video has been a little extra long compared to the traditional CBT Nuggets video in the series, but I couldn't think of a better way to group everything together and show you enough examples where you can see at least 4 different scenarios working through different classes of subnetting based on the number of networks. The benefit is you now have the chance to just sit down, let it soak in, review this video, review just sections of this video multiple times if you need to see some examples as you work through those practice problems. I'll also mention that when I created those practice problems, I didn't pull them from a book or something, or you know, oh, what should I do? I just made them up, and you can do the same thing. Don't think that those 4 practice problems are the only ones that you could do. Just think of a network that you have, 172.16.0.0, and then just say, I want 50, 90, 100 different networks, and then work out that subnetting problem and figure out what the result will be. The key is not only to master the subnetting, meaning come up with the subnet mask and find your network ranges, but to be able to do it quickly.